All right, hello everyone. Hope you're having a great week. So welcome to another week of Computer Science Club. Today we are going to be picking up where we kind of left off last week with searching algorithms. So last week we started with BFS, which is breadth first search, and then after this week we're going to be following it up with a very related algorithm called DFS, which is depth first search. Now, as a reminder, does anyone want to kind of sum up what were some of the highlights of BFS? It goes through every level one at a time. So that also means that it'll find the shortest path first. It's guaranteed for it to find the shortest path. DFS stands for depth first search. So that means that when given a starting point, it will first search through all nodes within the same branch before backtracking. So here is an example of, I'm going to show an animation again. As you can see here, it goes through this whole branch here, right? Before it goes back and moves on to the next level. Okay, so that's what I mean when I'm saying that with an infinite graph, DFS will get stuck basically, is because with an infinite graph, you don't actually have an ending node here. So it'll actually never reach that condition to go back to go to the next branch. The way that we implement DFS generally is with something called a stack. So if we remember last week, a queue is what we use for DFS, and that means that nodes are placed at the back and they're taken out from the front. Now with a stack, nodes are actually added to the front and they're also taken from the front. So this is kind of like the stack of plates, right? Where the new ones are put on top and the old ones, and whenever you grab a plate, you're also taking from the top. DFS is really useful for simulating conditions to find an end result. So for example, if you have a game decision tree, so you're seeing which moves take the least amount of time, or what are the possible moves to arrive at a certain scenario. It's really good for that. Or in any problem where the value of nodes might be recursive. So if the value of this node depends on this node, which also depends on this node, this would be something where you use DFS. Now, for many of the questions that you will be solving for now, there really won't be a real benefit for using DFS, but it has a lot of uses in more advanced algorithms, such as when you're pruning a segment tree, or for cases where the destination is known to be near the bottom, or when the graph is extremely wide. So if there's a lot of nodes here, this is really good because BFS will have to keep this whole section in memory, whereas DFS will just handle each branch separately. And just note again that DFS cannot be used to traverse an infinite graph, as your return condition right here will never actually be satisfied. So any questions about how DFS works? If that's the case, we can just move on directly into implementing this thing. So this is going to be the graph we're going to be using. It's virtually the same as the graph from last week. However, my example changed a bit. So I added just a node here that's lonely, doesn't have any connections here. First of all, we need to represent this graph. So does anyone want to make the adjacency list? We'll be using an adjacency list again. We don't always need to use an adjacency list to create these representations. You can always use an adjacency matrix or even an edge list. But for now, just because it's a little more easier to just set up here, we're going to be using an adjacency list. So let's go ahead and start our implementation here. The very first thing is, of course, you will need to have the representation of a graph. You will see that this week's example is very similar to last week's. So if you kind of got last week's, you should have no trouble with DFS here. Now, the thing we're going to be doing differently here is that we're going to be using a recursion as a way to kind of implement a stack, right? Because if we recall probably around 2 months ago when we went over recursion, right, everything gets executed in a stack. So we can kind of simulate that, and then we don't need to have another data structure to keep track of all the nodes that are upcoming. The very first thing is we're just going to define a function, and same thing as if we were to use a loop, we are going to set the visited of the current node to be true. And then we're also going to check if the node is currently at the destination. If so, we'll just say there's a path. And then return. Then after, if this is not the destination, we're going to simply add the adjacent nodes to our stack. All right, but the way that we add it to the stack is just by calling the DFS function here. So if we now run, here, I'll just do this. We now run this program. What we'll see here is if we say DFS from the start to the end, we'll have a we will have a path. If we just modify this, actually, let's modify this so we can say dest is here, just so that's a little more generic. Then what we can say is we can say DFS from the start all the way to 7, right? There is a path there. If we go back to our graph, we can see that we can actually go there, right? From 1 all the way to 7, that is a valid path. We can actually have it print out the current, let's go ahead and print it out actually. So let's just print out the node. We'll see how it's traveling. As you can see here, it goes 10257. And then after there are a few other nodes, so it keeps running, but it does find a path. Or loop to get to the next node. What do you mean? This is the same as last week's, right? The only thing is we're no longer adding to a queue. We're just going to call it and quote unquote add it to the stack. Here, if we just pull up last week's code, we can see how pretty similar this is, right? In fact, if we were to actually just replace this queue with a stack, we would have what we would call an iterative version of DFS. So to iterate means to go through a loop, right? So if we want to implement DFS with a loop, we can totally do that just by replacing this queue with a stack. But if we want to do the recursive version, this is how you're going to do it. So I didn't want to show the iterative version because it's literally just replacing the queue with a stack. This is the recursive version, and it's slightly easier to think about, especially if you're working with some problems that require you to actually, so for example, like if it's actually to calculate values all the way down to some ending, it's a little more easy to think about it through a recursion type problem than to think of it through a loop. Okay, so any questions about DFS or implementing DFS? This is a really short lesson, but I just wanted to kind of spend a whole week on it just to make sure that you guys understand not only DFS here, but also BFS last week, because I noticed that not many of you solved problems. I'm just gonna give you guys some more time to solve some problems this week. And then after we'll be going into another searching algorithms that's kind of similar to these, that builds off of these two algorithms. And then over the winter break, you'll have a decent arsenal of searching algorithms that you'll be able to do the decent majority of the questions on DMAJ or other contests, so you can practice over the break. So that's what I'm kind of doing here. I want to kind of sum this all up before the winter break. Make sure you guys really understand it. And then after, give you that whole Christmas break to practice these questions, because this is a very important concept. Knowing these searching algorithms is incredibly useful. So here's something that I want to introduce to you guys, which will be useful when you're solving this spreadsheet problem. So what most of you guys are doing is probably using recursion, right? We've talked about that before. However, with the spreadsheet, right, if you think about it, a cell can probably be referred to by multiple cells, right? You have cell A2, and then cell C2 says it's, for example, 1 plus A2 or whatever, right? If it's 1 plus A2, it's going to refer to A2, right? So that means it needs to calculate what A2 is. And let's say we have another cell called D7, and it has C2 plus A2. Well, then we also need the value of A2 again. If you're just going in this blindly, what you'll probably be doing is calculating the value of A2 over and over and over again, right? And that's something that we want to avoid, because that really increases the amount of time, especially if A2 depends on a whole bunch of other things, right? What we can introduce here is something called memoization. What this allows us to do is we store the returned value of some smaller operation. So then in a bigger operation, we already have that value pre-computed for us, and we don't need to do it over and over again. So all we're trying to do is reduce repeated work or completely eliminate it. So the best example here is the Fibonacci sequence. So if we define a function fib, right, and then we'll just say, so does anyone know what Fibonacci number is, right? Every Fibonacci number is obtained by summing the two previous numbers. So it starts off with 1, 1, then it goes 2, then it goes 3, et cetera, et cetera. So you take the two previous numbers, add them up, and then that's the value of the term. So we can use a program to find the nth Fibonacci number as follows. So this is a very classic recursion question. So we can just say if n is less than or equal to 2, it'll be equal to 1, right? Otherwise, we'll just return fib n minus 1 plus fib n minus 2. Does that make sense to everyone? This is a super simple recursion problem, right? So if we say fib at 1 is going to equal 1, fib at 2 is also going to equal 2. Now fib at 3 is going to equal 2, and then after fib at 4 is going to be 1 plus 2, which is 3, etc., etc. Right? And then we have 2 plus 3 is 5. So does this make sense to everyone? I'm hoping it does. Okay, so no questions. That's good. So if we were to do this kind of blindly, let's try to find the 50th Fibonacci number. It takes a while, right? This is not, it's going to take forever. Right? And the reason for this is because we're actually repeating calculations so many times. So let's say we're calculating, for example, a smaller number, like fib at 5. So the fifth Fibonacci number, what does it call? Well, it calls fib at 4, right? And also calls 3. Now, what does 4 call? Well, 4 then calls 3 and 2. 3 calls 2, then 1, right? And those two return. 3 calls 2 and 1 again. And 2 is just 1. So you see how there's a repeated thing, right? We already calculated 3 over here, right? This whole branch has already been calculated. So why calculate it again, right? You can see how the immense amount of duplicate calculations we have. So what we can do instead is we can actually store the value, right? This is just a strategy. It's not like a hard set rule of how you store it, but in general, we'll use a list and we can store, or a dictionary, and we can store this return value so that the next time we need to use f at 3, we'll already have that value. So we can just implement this very simply through a dictionary. Now, in other languages, you might want to use an array or something, but because lists aren't fixed size, we can't really do that quite easily. So we can keep the same return condition, right? But now we can say if our current index is in the memory, right? We'll just return what's in memory, right? We don't need to calculate it again. And otherwise, instead of directly returning, we're going to say mem at n is going to equal this. And then we'll return what's in the memory. So now what happens here is that every time we calculate something, we're going to store the result. Now, of course, this does take up more memory, but it drastically reduces the amount of calculations you're doing here. So now if we run this, we can see, we can do f at 50, fib at 50. It comes back right away, like almost instantly. We can do 100. Sorry. Right. That's still there, right? Fib at like 500. Right. That's super quick because it only needs to do unique calculations, which aren't that many, right? It's really the repeated calculations that take up so much time, right? We can go up to really high numbers. It returns so quickly compared to if we didn't memoize and then repeating things over and over and over again, right? Just look at our illustration here. We have almost half of the operations being duplicated, right? So through memoization, what we can do is we can drastically reduce our running times by just simply keeping track of stuff that we've already done. Okay, so that's the mini lesson here today. I would just encourage you to incorporate that into your solution, or you will TLE. So yeah, are there any questions about recursion with memoization? This is the basis of something else called dynamic programming, and we'll be going into that later after we're kind of finished with searching algorithms. So does that make sense? Does memoization make sense to everyone? Some of you are probably like, yeah, that's so obvious, but memoization, it's spelled memoization. Keys. So remember, a dictionary is mapping keys to values, right? So in this case, we're mapping the key, which is the Fibonacci number index, to the actual Fibonacci number. So we're just checking if we already have this number stored in our memory. I believe you can also just do in mem. I want to say, here we can just say, yeah, you can just say in mem, and I believe it also returns the key. So if you don't want to do that, you can just do that as well. Your homework this week is to finish the spreadsheet question. I just totally recommend you guys do that and really try to solve it. I think it's a really great, well-designed question, and it really covers a lot of topics. So if you're able to solve it, that means that you have a decent understanding of everything we've covered so far. And then after, also, if you're finished that, feel free to also check out the other problems that I posted. Those are also really interesting problems. And they're also a little more challenging. So it doesn't feel like you're just repeating the same code over and over again. And otherwise, we're going to go into some more searching algorithms, and then it'll be Christmas break. So that's it. Thank you guys for coming out this week. Again, if you have any questions during the week, feel free to just put that in junior help, and someone or me will be there to answer them. And otherwise, I hope you guys have a great week. See you later.